Hello, everybody. My name is Pavel Shamis. I also go by Pasha. I'm research staff at Oak Ridge National Laboratory. I want to thank organizers for inviting me over and providing the opportunity to talk about our OpenSHMEM effort. I'm part of a bigger team in Oak Ridge. It's called Languages team. We have expertise in different areas like compilers, message passing, networking, tools. We collaborate closely with the University of Houston. These guys maintain and develop reference implementation of OpenSHMEM. What is nice about Houston, whenever you have a problem, you may call there, Houston, we have a problem. University of Knoxville, Tennessee. These guys develop fault tolerance and threat safety model for OpenSHMEM. We work closely with Los Alamos National Laboratory. They help us to develop a file I/O model for OpenSHMEM. So I will talk about what is OpenSHMEM, a really brief introduction for the concept. I will talk a bit about history and current status of the effort. And then I will go over different tools and implementations of OpenSHMEM that we have in community. So what is OpenSHMEM? OpenSHMEM is communication library and interface specifications that implements and defines partitioned global address space programming model. So what is PGAS? This is OpenSHMEM interpretation of PGAS model. Essentially, we have different P's. P stands for OpenSHMEM process, processing element. We have two types of data objects. In other words, it's just memory. We have private objects, local memory. It's accessible only to the particular process. And we have remote accessible symmetric memory. Essentially, this memory that any other P may go, modify, access, read. Inside of this symmetric data object, we have actually two different types of data objects. One type is global and static variables. This is essentially C, C++ global and static variables that any other P may access, modify, read. And we have so-called symmetric heap. This is sort of pre-allocated heap. We're using shmalloc. Shmalloc stands for SHMEM malloc. You may allocate memory for a variable. In this we have like small example. We have x shmalloc's size of long. And using this command, you allocate memory for variable x on all P's. And once it's allocated, any other P may go read or modify this particular memory. And what is really nice, that symmetric objects have the same address. So in order to access the object, you don't need to go to other P and learn about where it's located exactly in the memory. This information you have locally because essentially the same address. On some platforms, it's not necessarily address, it's the same offset. But again, the same. Once you know base address, if it's the same offset easily without exchanging any additional information, you may go and access any variable. So OpenSHMEM, one-sided communication library in a sense that operations that the library exposes, it's one-sided means remote side doesn't have to be involved explicitly in communication. So you don't have to pull and be in library in order to progress communication. It uses symmetric data objects, as I described, to communicate between different processes. And main advantages, it's really convenient for irregular applications where the passive side doesn't have to be involved in communication. You just may go and read any address space. It's very latency driven. We really focus to make sure that software overheads are really low, and we may access the memory really fast. And as I show later on, it maps really nice on hardware, particularly RDMA hardware. SHMEM operations. I put here just some signatures of functions, some examples how it really looks. So API expose remote memory, put and get operation. Put, essentially you write to remote memory. Get, you read to remote memory. Here two examples, one for get, essentially specify target address, source address, where from you read, size, number of elements, and P, name of index of the P, where from you get the data. Put, very similar, but it works kind of opposite direction. You put memory to the target from the source. This is the size and destination P. We expose atomic memory operations. This is just one example, fetch and add operation, which fetch original value and adds some value to remote destination, target value, P index. We have basic collective operations like barrier, broadcast, some reduction operations. Nothing special here, it's very standard. We have memory synchronization operations. Essentially, we allow two different types of synchronization. One is global, it's essentially barriers. We have point-to-point operation where essentially you wait for some memory to change. The specification defines ordering operations for the memory, how we enforce order between different put and get operations. Also, we define distributed lock operations. And again, it's the same memory model. Essentially, for put gets, you just from any PE, you may go to other PE and access this global or symmetric heap memory. This is our mantra. First of all, keep it simple. The specification document is about 70 pages, it's that small. So it's a very small document, easy to read, we hope easy to understand. Keep it fast. And fast means that we want to offload everything to hardware. And if we will go back for a second, as you may see, put and gets applications, it perfectly maps on RDMA hardware. You have RDMA writes, RDMA reads. Atomic operations, it really maps nice on RDMA devices that provide atomic capabilities. Ordering operations, memory ordering operation, also with RDMA devices, usually they expose some ordering semantics. Let's go back and see what is the history of OpenSHMEM, what is the current state, and I will talk about future directions that we work on. So OpenSHMEM is not that new. It was introduced in early 90s actually by Cray Research, T3D system, and as you may understand from the name SHMEM, it pretty much was based on shared memory. In the early 90s, it was the programming model. All cool kids knew how to program SHMEM. Later on, it was acquired by SGI. They integrated into message passing toolkit. And other hardware vendors like Quadrix, HP, IBM, they released own versions of SHMEM. But the problem is that the interface was not defined by any specification, and there was no agreement between vendors. So they defined sort of similar interfaces, but not exactly the same. So if you want to, in 90s, to write SHMEM code, you end up to have a bunch of if-defs in your code. If it's Cray, if it's SGI, if it's Quadrix, and so on. So this obviously was not very convenient. 2011, OpenSHMEM was born. This was effort of Extreme Scale Systems Center in Oak Ridge and University of Houston. Essentially, the goal is to address the difference between SHMEM implementations. We released specification 1.0, which is essentially based on SGI SHMEM, original SGI SHMEM. The reason is that we have some legal commitments to make sure that we don't have any issues with SGI. But after 1.0 point, we have a freedom to change the specification in the way we want. So OpenSHMEM goals. Obvious goal is standardize the library, make sure that we go from different incompatible libraries. We define one common interface, and all vendors agree to support it, and community agrees to support it. Provide open source implementation of the specification, and this is obviously important for future extension of the specification. We need some open source platforms where a community may go and experiment with different concepts and ideas. Obviously, we want to extend the specification, make sure that it's ready for exascale system and future hardware. And in order to make it usable, we actually have to create tools that will help developers to use this library. Tools like analyzers, tracers, debuggers, and so on. And later in the talk, I will talk a lot about tools. And we want to create OpenSHMEM Community. It's this community effort. We want to vendors and labs be involved in the effort and make sure that the specification goes in the right direction from community perspective. Let's continue in the history. 2012, we continue to develop reference library. We introduced validation test suite, essentially tests to validate that your implementation is correct. We released 1.0D of specification. It's very minor improvements. We started to see more and more vendors involved in the effort. And as I mentioned, we started to work on tools, OpenSHMEM Analyzer, DDT Debugger provided support for OpenSHMEM, tracers like Tau tracer and SHMEM tracer, SHMEM Tau tracer enabled support for OpenSHMEM. 2013, we have new tracing tool. It's very popular in MPI community, one-peer tracer tool. And in order to enable high-performance implementations of OpenSHMEM, we started work on UCCS, which is low-level communication middleware library for different network interconnects. And we released 1.e. Again, this is minor improvements. So where is OpenSHMEM now? We have a website, openshmem.org. You may go to the website and find OpenSHMEM reference implementation specification. We have mail list where you may ask questions, send your ideas. Very recently, we released, months ago, we released OpenSHMEM 1.1, this more substantial changes. It's still based on SGI, but we improved format of the document. We made it more readable. Better introduction, better description of functionality, much more examples. And at this point, 1.1 still open for comments. You may go read, and if you see some issues that you want be fixed in 1.1, it's still open, we still may do it. And we started to work on what we call 1.x, and I will show later our roadmap, which is much more substantial changes for the specification. It's no more HGI-SHMEM, it's essentially new SHMEM. You may contribute to the specification. We have Redmine. This is a ticket management system. You may go to the website, submit proposals, submit ideas, open bugs. Very nice, very convenient tool. OpenSHMEM Community. So these days we have much more organizations involved in the effort. From academia side, University of Houston, ICL, this is University of Knoxville, Tennessee. DK Panda talked yesterday about Ohio work there. Dresden, Florida. We have broad support from vendors, Intel, obviously Mellanox, NVIDIA, HGI, Cray, HP, DDT. And we have all the government organizations involved in the effort: Oak Ridge, Los Alamos, Sandia, Aragon, Department of Defense, Department of Energy. OpenSHMEM implementations. We have a lot of different implementations. Different in sense from different vendors, but this time they expose the same API. So proprietary implementation, HGI-SHMEM, Cray-SHMEM, IBM SHMEM, HP SHMEM, Mellanox scalable SHMEM. We have legacy SHMEM, which is not OpenSHMEM compatible, but it's really a cool implementation. We take a lot of ideas from Quadric SHMEM, but this is not OpenSHMEM. And we have open source implementation, obviously OpenSHMEM reference implementation from University of Houston, Portal SHMEM, this is SHMEM implementation for portal devices. This is a relatively new work, OSHMP, from Aragon guys. Essentially, they want to implement SHMEM on top of MPI. You have OpenSHMEM implementation within the OpenMPI code base. MVAPIC, Ohio State University, again, it's the same implementations that DK Panda showed yesterday. TSHMEM and the Gaptor SHMEM from University of Florida. TSHMEM, I think, stands for Talera SHMEM, actually. Let's talk about future of OpenSHMEM. Since it didn't change too much from 90s, now we have a lot of work to do to make sure that we adjust the specification for new technologies that we have now. So this is a tentative roadmap that we plan to follow, but this is just essentially our to-do list of ideas. First of all, we want to fix naming space, introduce finalized function, consistent data type support, version information. These are relatively minor changes. We plan release it relatively soon because it's easy to do. We have planned for more aggressive changes, like non-blocking communication for put, gets, atomic, definition of teams, support semantics. In 1.6, we consider to introduce non-blocking collectives. 1.7, thread safety, but we actually get a lot of pressure from community for thread safety. So we are going to increase priority of this work, and we'll try to release it as soon as possible. And we have what we call OpenSHMEM NG 2.0, and essentially in 2.0, most likely we will break backward compatibility, and we introduce very, very substantial changes to the specification, like fault tolerant, exit codes, I operation, tools interface, and so on. Again, you actually, if you have any ideas, you may go to openshmem.org, to Redmine website. We have form where you may essentially put requests for extension So if you have ideas, if you're interested, please go and do so. And now we will switch to what we call OpenSHMEM Eco-system. We have a nice diagram over here that presents our vision, how we see it, that essentially we have OpenSHMEM reference implementation, we have UCCS, which is network layer for OpenSHMEM. And then in chain, we have tools like tracers, analyzer, and debuggers. And all the things should work together, and we have to collaborate in co-design to make sure that it works smooth. So let's talk about OpenSHMEM reference implementation. As I mentioned, developed by University of Houston with collaboration with ORNL, provides up-to-date open source implementation of specification. On network side, it's based on GASnet, and recently we introduced UCCS, which is pre-production support high-performance network interface. The specification focuses on providing full coverage of the specification. Essentially, you want to make sure that you have all the functionality in the implementation. It's not necessary, at this point, it's not necessarily focused on high performance, but with UCCS, we aiming to address this goal. And it serves for us as a platform for development of different extensions for experimenting with the model. 1.f version is available on the OpenSHMEM website. I think it's BSD licensed. This is about all about OpenSHMEM reference implementation. And I will go to talk about UCCS. And I actually really heavily involved in this project. So what is UCCS? It stands for Universal Common Communication Substrate. And the idea here is that we have MPI communities that invested a lot of time and resources in development very optimized network layers. So the idea is let's take this internal communication layers of MPI, extract it to standalone library, communication library, and make it available for broader HPC community, like OpenSHMEM, but not necessarily OpenSHMEM only. It might be useful for other potentially programming languages, other programming models. Initially, the work was based on OpenMPI. Essentially, we reused middle communication layer of OpenMPI. We extracted it to a standalone library and started to modify this layer to make sure that it addresses different needs of different programming models. This is overview of work that we are doing. In red, I marked actually where the work happens right now. So UCCS is sitting between OpenSHMEM layer and driver or hardware. OpenSHMEM library, like reference implementations, talks directly to UCCS. On UCCS level, we have different communication channels. We're doing a lot of work with verbs, which is interface for InfiniBand devices. Eugenie, this is Cray interconnect. Cray API for Eugenie and Gemini interconnect. Gemini and Aries interconnect. We're doing a lot of work for shared memory. And later on, I will talk about some of our work about using UCCS directly on hardware. In UCCS library, we actually decoupled the network layer from runtime environment. RTE stands for runtime environment. In this context, what we call runtime environment is a service that starts processes on machines and provides very basic out-of-band communication services. This very thin layer, and essentially under this layer we use ALPS, this Grace runtime environment, Slurm, Sticky is internal Oak Ridge runtime environment, or ORT is this runtime environment from OpenMPI Community. You may find much more information about the project on the website. We also have mail list. If you have any questions, feel free to ask, to send to the mail address. This is a list of our goals. And essentially what we want to develop with UCCS, it's really low-level communication abstractions that supports multiple programming models and at the same time provide support for multiple network interfaces. We have like a diagram here. Essentially, we want to support programming models like OpenSHMEM, UPC, Extend, Chapel, MPI, and underneath the intent is to support different interconnects, Gemini, C-Star, InfiniBand, BlueJean, and so on. And idea essentially is to reuse the same code for different programming models and create a bigger community that may work on this network layer. This relatively new goals that we have on the list, essentially, how do we expose information about power consumption that we have from devices to users, and how upper layers may take advantage of this information. We want, with this layer, we want to enable support for a hybrid programming environment efficiently, where we have efficient memory location, essentially sharing of resources between different programming models like OpenSHMEM, Plus, MPI, or whatever. Again, provide flexible API, broad HPC community support, runtime support for multiple network technologies. Essentially, in runtime, we want to have the switch and say, okay, I want to run on InfiniBand, I want to run on Gemini, or I want to run on both. We want to provide interface for con-translation tools like CAF or UPC, since we have compiler people in the team. We always get comments like, oh, this is very difficult to translate for compiler. Make sure that you change the interface and make it compiler friendly. Obviously, performance. And as we go through the process of building the library, we define specifications that describing the library. The intent is that potentially vendors may provide their proprietary implementations of this interface. This is a very brief overview of UCCS API. We have active message API, contiguous, non-contiguous messages. It targets programming models like UPC, Core Fortran, MPI. We have RDMA, pull to get interface, again, contiguous, non-contiguous memory, atomic operations, collective API, and runtime APIs that connects to different runtime environments. And on OpenSHMEM side, we actually use only RDMA, atomic, collective, and RT. Our long-term goals, direct network hardware support. And in order to achieve our really high performance goal, we have to collaborate closely with hardware vendors in order to make sure that the interface maps really well on the hardware. We work closely with compilers guy, and we want to build communities that will support this interface. A little bit about UCCS over InfiniBand. Actually, I have to put mark here, don't try it at home. So essentially what we did, we ported UCCS directly on top of InfiniBand hardware. We don't use verbs driver. Essentially from UCCS layer, we directly talk with hardware abstraction. And in other words, it's doorbell on PCI Express to the device. Here we have some preliminary evaluations that we did. Essentially, typically you have open fabrics, verbs driver, you have some middleware, and on top of this you have OpenSHMEM driver. It depends on the platform, but about 100 nano, communication middleware another 500, and essentially with a prototype version of UCCS, we may cut all this paths and directly access hardware somewhere around 70 nano. We don't plan to replace OFED. OFED it's Open Fabric interface, verbs interface for InfiniBand. But it's interesting investigation because it allows to minimize the software overhead. Maybe in future we may introduce it as a standalone ULP and Open Fabric that is designed for HPC community. And how do we cut the latency? Essentially, we avoid some duplicated logic in the layer, like verbs interface was designed as a very generic interface. You have single API that has put, get, atomics inside of the library. Since in OpenSHMEM, we already made the decision on the application layer, what API is used. We may shorten the path. We know that from OpenSHMEM, we should go directly to put logic and essentially avoid all these if statements in critical paths. The same true for thread safety, for logs. The same true for credit counters. And actually error handling as well. We work closely with Mellanox to make sure that OpenSHMEM and UCCS maps really well on RDMA hardware. And essentially, if you look at InfiniBand specification, it maps really nice on OpenSHMEM. You have RDMA put and gets, the same OpenSHMEM and UCCS, atomic operations, and in a minute we'll talk about core direct work collectives offload that we did together with Mellanox. So Mellanox core direct and Cheetah framework. The goal of this effort was essentially improve performance of collective operations, not just for OpenSHMEM, for all HPC community, scalability of collective operation, enable overlap of communication, computation, and reduce the effect of system noise. You have some links here to Cheetah framework website. The work was supported by Department of Energy, Oak Ridge, and HPC Advisory Council. So, a little bit about history of the project. Actually, Gilad was involved in the effort from very beginning. The idea is very simple. If you look at applications, you will see that collective calls used a lot. And very often it's one of the bottlenecks for scalability of application. If you look at algorithms of collectives, it's usually some sort of trees, n-array tree, or some hypercube-based algorithms. And it's very easy to translate for each node in this tree, translate the operation to some chain of tasks, which essentially send something, receive something, or wait for something. Once you have this so-called software task of operations, it's actually possible to map it to hardware calls and essentially transfer all this chain of operation directly to hardware, and hardware will take care of all the progress. We started with Connectix 1 devices. It was mostly firmware prototype. Connectix 2 and all following devices have hardware support for this. Really nice. We developed a software layer in OpenMPI. and later on we worked on more generic layer, which is Cheetah. So what are core direct operations? These are standard operations in InfiniBand spec, and essentially we extended for it for few more operations like send enable, receive enable, but probably the core operation here, it's wait task. Essentially, wait task allows to wait for completion of some operation. And using the wait task, we may build this chains of operation. Receive, receive, wait for this receive happen, start send. So how does it work? Essentially, in typical collective implementations, what happens, you have this algorithm design on software layer, and for each send or receive operation, you go to hardware, you do send, you wait a bit, you go back to software, send, back to software, send. So you have to have a lot of iterations, a lot of steps here between software and hardware layers. With hardware offload, essentially we pre-build the chain of operations, we push it down to hardware, hardware progress everything, essentially internally hardware executes all the steps, and we get eventually completion, everything is done. This is from one of the papers, very preliminary evaluation of the work. Essentially, the idea here is to show that with hardware offloaded collectives, we provide a lot of overlap, up to 96% essentially. You push the work to hardware, and then you're free to do your own calculation and use the time to do some useful work instead of spinning on CPU. Later on, we extended this effort to so-called Cheetah framework. Right now, it's some sub-part of OpenMPI project. Essentially, with Cheetah, we support multiple hardware technologies like core direct from Mellanox, shared memory, Eugenie from Cray, and generic point-to-point, which is essentially based on send-receive semantics. And key concept here is that we essentially build hierarchical collectives. We have basic collectives operation on shared memory layer, like CPU socket. We have next layer socket subgroups. We have upper layer and so on. Essentially, on each layer, we execute custom design collectives and build hierarchical collectives. Essentially, it goes from very low level from socket. We build this hierarchy of calls. We go up and then we go down. And the idea that right now we work to make the Cheetah standalone library, and we plan to integrate it into UCCS project. Essentially, this will provide collectives interface in UCCS that I discussed earlier. Let's talk a bit about tools like Analyzer. This really cool project that we started in Oak Ridge, and basic idea, let's use compile time analysis, essentially the same analysis that already we have in compilers, to help OpenSHMEM application developers to find bugs and potential issues. Essentially, this list of supports that analysis in Analyzer. Essentially, we know how to generate call graph of OpenSHMEM calls. Semantics check essentially if you use correct order of OpenSHMEM calls, if you initialize the library before usage, detect correct usage of symmetric variables. Essentially, if you by mistake trying to access some variables that not in symmetric heap, Analyzer may detect it in warn user. It tracks allocation of memory, essentially may help you to detect memory leaks. it detects synchronization phases. Essentially, it helps you to find issues like inconsistent calls for a barrier, which essentially may block the application. And essentially, this group is constantly involved in our extension development to make sure that whatever interfaces we introduce, it's easy to use with the tool and easy to detect errors. This is a screenshot of some example. Essentially, this is some buggy applications that we compiled with SHMEM CC, and it warns that SHMEM flow output operation trying to access some memory that was allocated with malloc instead of shmalloc. Right now, the tool is based on Open64 compiler. But we work with compilers, vendors, to transfer the technologies to other compilers. Some other examples. This is analysis for unaligned barriers. Essentially, this is SHMEM barrier all call, different if statements. We have a compiler to analyze this if logic and essentially make sure that all barriers logically aligned. One more example. Essentially, in OpenSHMEM, atomicity of operation guaranteed only if you use atomic operation for a particular memory region. So we have some buggy example where the same address is accessed using put operation and atomic increment operation. Compiler detects this inconsistency and essentially warns user about this issue. One peer tracer. You may know this tool from MPI world. Essentially, we work closely with Dresden University to make sure that the tool supports OpenSHMEM. It's actually a really, really nice tool. You have this all nice graphical representation of what happens in your application, like function calls, communication synchronization. You have runtime statistics, how much time you spend in each OpenSHMEM call. You have some statistics about data transfer. Very convenient tool, easy to use. Our developers use it a lot. DDT. So DDT essentially is very convenient parallel debugger. It supports OpenSHMEM. Virtually, it supports all proprietary implementations and most of open source implementations. And essentially, it's like any debugger, but parallel. You may go and see each PE, where it in the code, what is the status of variables. It has very convenient query operations where you may read values of different variables from multiple PEs. Very nice, very convenient. Actually, personally, I use the tool a lot for a debug of UCCS code. This year, we had OpenSHMEM Workshop. We released proceedings. You may go to openshmem.org and see all the papers that were presented at the workshop. A lot of vendors attended the event. Actually, we planned to have it 2013, but because of challenging government budget situation, we suspended it to 2014, and then, because of challenging weather situation, we almost canceled it, but nevertheless, we made it. It was in Annapolis, Maryland. We plan to have next year a similar workshop. So please check OpenSHMEM website we'll post, if we will have this event, we'll post on the web. I want to thank our sponsors, Department of Defense and Oak Ridge National Laboratory for supporting our work. And we have some time for questions.